We continue. Next speaker will be Konstantin Ryutin with best m-term approximation of the step function and related problems.
So I'd like to thank the organizers for this opportunity to make a talk at this very interesting conference with lots of interesting talks and people. So let us start. I will talk about a joint work with Boris Sergeyevich Kashin, Yuri Malykhin, and me from Moscow. So, the main point of the talk will be the question of the order of decay for Kolmogorov weights of Sobolev classes, the case of small smoothness, and similar problems in computer science and some variations of these problems. So the main hero of the talk will be the class of step functions in one variable or several variables at one occasion, and closely related classes of functions of bounded variation, or W11. So first of all, let us recall a definition for X, a linear non-subspace, and some subset of X called W. We recall the definition of the deviation of W from L. So L is a linear subspace. L is a linear subspace. So here is the usual definition of the deviation. We try to approximate our subset W, and we find an element of this set W which is the worst case from the approximation point of view by this subspace. And after it, we try to find the subspace which approximates our set W in the best way. So here is the usual definition of the Kolmogorov n weight for a set W. It's written here, so it's an infimum over all linear subspaces of dimension n of this deviation. So this notion was introduced by Andrei Nikolaevich Kolmogorov in 1936. As I understand, the motivation for this definition, or for some similar ones, were the idea to measure somehow the complexity for functional classes, especially of several variables. And one of the most glorious applications of all these results and approaches was a proof of the smooth case of a well-known 13th Hilbert problem on superpositions of functions. So, and also some very interesting questions which were raised in 50s about tabulation of functions and so such possible applications which are now very, very popular. So all this kind of stuff was very intensively studied since 60s after seminal papers by Tikhomirov and Kolmogorov. And one of the main problems was to find sharp orders of decay for functional classes: Sobolev, Besov, Hardy, and so on and so on and so on. So an enormous amount of results of papers by different authors in different countries. In order to achieve these results, very many different kind of techniques were applied, from harmonic analysis, functional analysis, probabilities, and so on. So and now we see a certain a huge activity in this area, which is stimulated by research on similar problems in computer science and applications, such as compressed sensing and so on and so on. So, and here is another definition which comes from the area of computer science. It's the definition of approximate rank or epsilon rank of a matrix. Let A be a matrix, and we fix some epsilon greater than 0. Here is the definition. We are looking for another matrix of the minimum possible rank, such that each element of these two matrices differs by epsilon at most. So we fix our matrix A, we somehow try to manipulate with its entries, but in a way that the error is not greater than epsilon. And we try to minimize the rank of the matrix which we can obtain in this way. So the motivation for this question, also for this problem, for this notion, so some applications in machine learning, statistics, data compression, nonlinear programming, and some kind of numerical methods. So usually it's much easier to approximate things in L2 norm rather than in L infinity. So for the case of this matrix problems, we arrive at the Frobenius or spectral norm, where it is known how to solve this problem, and the answer is given by the truncated singular value decomposition of the matrix. But we are interested in this talk. We are interested for the problem of the epsilon rank in an L infinity norm, where it seems more difficult. So in order to approach this problem, we can use different tools from several areas, from the traditional theory of Kolmogorov-Weitz, so some ideas from functional analysis, geometry of Banach spaces, probability, and so on, or some ideas from this complexity of computational problems. Well, there are some other notions similar to this epsilon rank. One of them is the notion of rigid matrices. So here it is written, we are looking for the minimum rank of the matrix B such that A and B differ in at most k entries. So we are not trying to approximate our matrix with a matrix of a small rank. Rather, we can somehow manipulate with all possible entries, but no more than k in the number. So I mentioned one of the problems in this area. It's I think rather known to specialists in computer science. So somehow one is encouraged to construct an explicit family of rigid n by n matrices. So a family of matrices with this condition. And one of the results, which was somehow surprising, that Walsh matrices were not rigid. That's one of the fresh results in this area. So another notion which is also popular is the signum rank. We start with a matrix A such that no element of it is 0, and we can vary its elements in order that we do not change its sign. So the question is how to minimize the rank. This is known as a signum rank quantity. So I mentioned some authors. So it's Lee, Schreibman, also Alon was interested in this kind of problems.
So this suggests the notion of approximate Lee Schreibman.
Yeah. And also this mentioned two authors, and also Naga Alon and some other were very active in all these kind of quantities. So they studied signum ranks for different matrices and so on. So now I try to show that these two quantities, they somehow related. Namely, we take our matrix A, n times M matrix. We consider the set of its columns, the set of vectors A, G. And then they see that there is this equivalence. So epsilon rank of our matrix is not greater than n small, if and only if. The Kolmogorov-Weitz of the set of this set when we can take the set of the columns, they take minus this set, convex hull, and then we can have this equivalence. So here is our first example. The approximate rank of the identity matrix. The problem of estimating this quantity is equivalent to the problem of estimating the Kolmogorov width of the octahedron. So here we see this B1n. As usual, As usual, so we set the usual definition of the LP ball in Rn, and here we have this L1 ball or an octahedron. So in order to estimate its quantities, one should try to use methods related to both of the two equivalent notions. From the theory of approximate rank of the matrix, we learned that there is this quantity called gamma 2 norm of the matrix. Here I wrote its definition. I even wrote two of them. They're equivalent. One is the when I factorize my matrix as a product of C and B, and I try to minimize the following product of norms of these matrices. And the other one is more easy to grasp at first sight. So I simply try to write all the elements of my matrix as scalar products. I try to find a system of vectors x and another system of vectors y in the same Euclidean space of some unknown dimension, and I try to find them in such a way that to minimize all possible products of their norms. So, and this gamma 2 norm is very popular in all this kind of research, and there is a very useful relation. I wrote it here, which will be important for us. So, and from the theory of width of a convex body, we can apply the techniques of entropy, volumes, orthomassivity. I will talk about it later. Some kind of stuff from harmonic analysis, and from trigonometric approximation, and many other. So for the epsilon rank of the identity matrix, we have to estimate this width. So it's the width of the octahedron in L infinity matrix. So as all of us knows from his first year, the most simple matrix is more or less the identity matrix. So when they introduced this notion of the epsilon rank, the first candidate to look and to try to estimate is the identity matrix. But here they arrive at the problem which is not solved, and the result is not known even today. This order of the decay of the Kolmogorov width of this octahedron is unknown. The problem is with extremely low dimensional approximations. So, and I have to tell that first estimates on this quantity were obtained by Ismagilov, Kashin, Herlich in 70s, and I think that the best result up to now was obtained by Gluskin in his paper called "Octahedron is poorly approximated by random subspace." So he proved the best lower bound. I wrote it here, and he conjectured that in effect it's the true order. but it's not known even today. So, and also there is another result in this paper. It's the calculation of the approximation given by random subspace. So, and this you can see that these random subspaces are not good enough in the regime of extremely low dimensional approximations. So, but we will be interested in another matrix. So here is the main point of the talk. So we will deal with this matrix. It's also a very simple one. It's a triangular matrix of zeros and ones. So here is the definition. So the corresponding set is what we call the skew octahedron. So it's a convex hull of this kind of vectors. We take several ones and then zeros. So and we see that the question of estimating epsilon rank of this matrix is equivalent to obtaining good estimates for the corresponding set for the Kolmogorov weight of the corresponding set in L infinity norm. So the motivation for these studies. The main motivation, so it's not only the main motivation, but it was the starting point of all this activity for us, was the question of the decay of the following weight. I think it's the only one case which is not covered by intensive studies in 70s, 80s, and even 90s for the decay of the Sobolev classes. Namely, it's what is in one dimension. Namely, it's what we call the case of small smoothness. So this class W11, we have the estimate from below and from above, but they differ by a square root of the log. So here I did not put it on the in the presentation, but this result is due to Kulanin, I think, yes. These estimates, they are due to Kulanin in the late 80s. So, and we made a tiny improvement of this estimate, so we got rid of this epsilon here. How it does it look? So we got rid of this epsilon, and we made a better, lower estimate. It's the first result. So, and I think it was a rather interesting lemma which we used in order to obtain it. So I decided to put it in the presentation. It reads as follows: for any matrix M whose rank doesn't exceed n capital over 4, we have one of the two following alternatives. Either many elements on the diagonal are far from 1, at least a half of them, or the matrix itself is far from the identity matrix in the Frobenius norm, in the following sense. It's written here. And by some construction which used at some place this lemma, we managed to get rid of this epsilon in the low estimate for the W11 Kolmogorov weight in LQ norm. So, but when we deal with the Sobolev class 1,1, it was more convenient for us to consider the functions of bounded variation from the point of view of Kolmogorov weights in LQ, which we considered 2 slides earlier. It's the same. And this class of functions of bounded variation is generated by the set of step functions. And as I said at the first slide, it's the main hero of the whole talk, so the set of step functions and how to approximate them. So the function is a very simple one. It is 1 for on the segment from 0 to t, and then it's 0. So Viktor Konovalov in 2003 pointed out the discretization for this case. So we can work not with a functional class, but rather this Kolmogorov-Weitz of our skew octahedron for this range of dimensions. So we can fix epsilon, say epsilon equal to 1 over 3. It is known that this epsilon 1, 3 rank of our matrix can be estimated from below and from above by second power of log and third power of log. And Nagar-Alon, Lee, Schreiber, and Vempola derive this from known results. We tried to improve this estimate, but somehow we didn't manage to do it yet. So, and later I'll talk about some generalization of this result to the multivariate case, and also I'll talk about some approaches to this kind of questions. Firstly, I'll talk about the upper bound for trigonometric approximation, and I'll show finally that one can prove a third power of log lower bound for some reasonable random method. So the first approach is the notion of orthomassivity introduced by Kashan in 2002. We can take a subset of some Hilbert space H, and we are interested in the following quantity: the sum of scalar products over all possible, and some supremum over all possible orthonormal systems of vectors phi g, or in an equivalent way we can define it in such a way. One can show that for the set of the discrete steps, that's just our functions from the definition of our skew octahedron. One can show that this orthomassivity behaves itself like n to the power n to log n. And namely, we can take for phi g the row of the Hilbert matrix. So it's rather easy to see, to evaluate, to estimate this scalar product. And so I try to give you the idea of the proof of this result. So if the steps, our steps f, g, are well approximated by some vectors zg, then the sum of scalar products should also be large. On the other hand, as we try to approximate our system by vectors from a low-dimensional subspace, Ln, we can make these estimates, and using the fact that the norm of the Hilbert matrix is bounded by some absolute constant, we finally arrive at its result that in order to achieve a good rate of approximation, our dimension should not be lower than second power of log, to second power of log. So this generalizes to the multivariate case. we can consider the vectors in this huge dimensional space, r to the power n power d. And in this space, there is a system of indicators of parallelepipeds. I wrote the definition here. And one can show by using some tensor product construction and generalizing the previous considerations from the previous slide that if we have this upper estimate for Kolmogorov-White, then the dimension should be not less than log to the power 2d n. So, and some words about upper bounds for this epsilon rank. One of the popular methods introduced by, I think, Alon and his co-authors is a random method. So we have our matrix A, and this matrix is represented somehow as scalar products of two systems of vectors, x and y. So we can consider a projection of all these vectors on n-dimensional random space, just as it's the approach from the well-known Johnson-Lindenstrauss lemma. And for appropriate choice of n and this random matrix U, we have this identity, maybe equality, approximate equality. So the scalar products of x and y is more or less equal to the scalar products of their projections, with high probability. And so we obtain that our matrix A is approximated by a matrix of rank not exceeding n small. And after it, we can apply estimates, for example, from a paper by Alon and Kvartak from 2016, which contains rather precise estimates for such a situation. And so we can obtain an upper bound for epsilon rank of our matrix A in terms of the gamma 2 norm, which was mentioned several slides before. Well, so now we come to the last part of my talk, which deals with trigonometric weight. So what is trigonometric weight? The easiest way to see it is in functional classes. So when we are dealing with approximation of some functional class, we can try to find the best subspace of dimension not exceeding n small. But if we restrict ourselves to not to all possible subspaces, but only to subspaces generated by some good basis, for example, trigonometric basis, when we arrive at this notion of the trigonometric weight, I wrote it here in the situation of finite dimensional vectors. So here k is simply the discrete exponent, this one exponent is written in the middle of the slide. And also here I recall a well-known notion of best n-term approximation according to this system of exponents. So I try to approximate my element x with the best possible linear combination of n small exponents with some coefficients. So it was Belinsky, I think, who showed that the problem with estimation of Kolmogorov-Whites of this class W11 in LQ, which we are dealing with, can be solved if we consider, instead of the Kolmogorov-White, the case of this trigonometric wave. And in this case, he obtained the order of decay. It's written here. It's n to the power minus 1/2 log n. So, and in our case, when we are dealing with a Q octahedron, the problem with trigonometric weight boils down to n-term approximation of a fixed function. This fixed function is the sum of sinuses kx divided by k.
Just one step function.
Yes, it's just the Fourier series for one well-known function. So, and we can make use of the general theorem on sparse approximation by Devor and Teblikov from 1995. It's a rather general statement. So we take any subset of the cube, n-dimensional cube, of cardinality m capital. We introduce this norm x, y, and then we have this estimate. So the estimate for the approximation, so the best n-term approximation. So it's like that. And if we apply it for the trigonometric setting, we see that log to the power 3 of harmonics suffice to approximate all steps functions. So, and the corollary from our previous estimates using orthomassivity and these considerations, that is that for a multidimensional case we can obtain this statement. So now to the, I have how much?
5 minutes
Okay.
minus epsilon.
Okay. So it's several slides I left. So, and also I can mention a result by Temlyakov that one can construct this practically optimal n-term approximation by a constructive method, namely using some kind of some version of the greedy algorithm. If I it's another result. So the last part of the talk, in the last part of this talk, I will deal with random constructions for this problem. So suppose we want to get a sparse approximation for a vector x. One of the ways to consider selectors, so random variables, which are very simple. Each variable is can take only two values. One of them is 0 with high probability, and the other one is written on the slide. And so the expectation is 1. So if one can prove that the norm written on the slide is small with high probability, then one sees that this vector x will be approximated by the sparse sum. So the sum will be sparse and the approximation is somehow controlled. So here is the result. So it can be shown, it's an exercise in applying deviation inequalities such as Bernstein inequality, so that this method produces the desired approximation with the number of harmonics about third power of log in our situation, but not better than that. So it's just the last part of the talk. So as trigonometric polynomials are shift invariant, so in our problem we can only consider one model function. It was written before. And here is the statement. So let eta k be random variables such that the expectations are 1. There are some estimates for the moments of these variables, and delta k are the probabilities that these variables are non-zero. Then we have the following alternatives. Either the sum of this delta k is not less than third power of log, or the average deviation is at least some absolute positive constant c. So this shows that one cannot using a rather general method of obtaining these random constructions, one cannot get optimal result. So one cannot exceed this, somehow close this gap between log to the power 2 and log to the power 3. So and here is some very useful inequality which is important in this proof. It's an inequality from the paper by Kashin and Temlyakov from 2007, where they introduced this notion of QC norm. So I use dyadic decomposition. I consider the following quantity: the expectation over all possible choices of random signs before this dyadic blocks. And we have for any function from L1 on the one-dimensional torus or circle that this QC norm is bounded from below by the sum of L1 norms of the summands. And it's a very, very powerful inequality. So, and in our in our situation, we can somehow control this one norm by some kind of harmonic analysis construction by L2 norm and arrive at a result. So, thank you for your attention.
Thank you. Maybe one long question or two short questions? Or any indeed?
I think so. The answers is important.
No question? Oh yes, there we are. One question.
In the beginning, the problems with matrices, like what is the minimum number of entries to change and so on. Is there some practical algorithms to do that?
So I'm not a specialist, but all these people from computer science, they are just looking for algorithms. So I'm sure that some kind of algorithms are present in these papers.
So in this group of Alon, there must be something
yes.
practical, so to say.
Absolutely.
Well, this notion when you change the fixed number of entries, it's far much complex than the epsilon rank. So it's simpler. You have convexity here.
Yeah, sure.
And they study questions like NP hardness or not, so such kind of questions. But that's not the case here. So here it's more like functional analysis and so estimates.
I have a short comment. I'd like to thank you for reminding us that width in Russian is a beautiful word of approximation.
Seen this on the second slide or so.
Yes, it was written deliberately.
I've seen that. Thank you very much. Reconvene at 11.
Where is it?
11.
Oh, yeah.
There it is.
Oh.
There it is.
Oh.